Now that we've learned about polynomial functions and how to locate their zeros, we're going to look at rational functions and examine them in some detail. Now, rational functions, as you know, are polynomials over polynomials. So we'll spend the time now looking at the various possibilities here. We'll start by looking at general rational functions, and we'll move on eventually to learn how to graph these. So, general rational functions. Definition. So we have this down for the record. A rational function, big R of x will be the terminology, the symbolism that we use for rational functions here, has the standard form. Of course, all of these forms that we get are standard form. That will help us analyze them later. R of x will be written as P of x over Q of x. And I'll refine the forms of P of x and Q of x a little later, where, what are these? Where P and Q are real polynomial functions. And you remember what that means? That means they have real coefficients. So real polynomial functions. And Q in particular is not the zero function. So it's not the function that's identically zero all of the time. It's not the zero function, and since we can write it down now, let's do so. What is the domain of R? Well, it's obvious that the domain of R is going to be every real number except those that make the denominator 0. So we'd say all the x's in the real numbers such that Q of x is not equal to 0. Now, even when Q of x is not the always 0 function, it can be 0 sometimes. So we want to eliminate x's that cause that to happen. So that's the definition of the general rational function. Let me show you a little example here, just to illustrate what I just indicated there. Suppose we look at the rational function R of x equals 2x squared minus 4 over, say, x plus 5. Now, in this case, what would we say the domain of this rational function would be? Well, it's clear that it's going to be all the numbers that avoid making the bottom 0. There's only one number that causes the bottom to be 0, that's minus 5. So this would be the set of all the real numbers where x is not equal to minus 5. So that wasn't very difficult there. That's what a rational function is, and that's how we indicate its domain. But there is something I wanted to warn you about here, because you have to be careful about that. Here is the warning with a specific example. Suppose R of x is the following: x squared minus 1 over x minus 1. Nice, simple rational function. Let me factor the top because I can. It is a nice difference of two squares. So I'll go ahead and write this as x minus 1 times x plus 1 all over x minus 1. Now, your instinct here is the instinct that you've developed from your algebra to cancel x minus 1 and x minus 1 and allow yourself to say that this is equal to x plus 1. Well, you should realize that that's not right in the case that x is equal to 1, because then both of these are 0 and you'd have division by 0. So, but there's a more important fact here that has to do with these being functions. If I call this x plus 1 f of x, these are not equal. And the reason that these two functions are not equal, even though the algebra suggests they might be, is because of exactly that division by 0 problem. It causes the domain of R to be different from the domain of f. And functions with different domains are different functions. So these are not equal because the domain of R is the set of real numbers, x in the real numbers, such that x is not equal to 1, because that would make the bottom 0. And that is not equal to the entire set of real numbers, which happens to be the domain of f, this function on the right. See, this function, any real number can go in for x. So the domain of R and the domain of f are not the same, and as a result, the functions cannot be the same. So you have to be careful when you try and divide things like this, that you only divide when you know that x is not equal to 1. Okay. Well, we can avoid the problem that occurred on the other page if we're a little bit careful. If there is no possibility of division, then we don't have to worry about the problem. So here's the definition. R of x, which of course I can write as p of x over q of x, where p and q are polynomial functions, actually real polynomial functions. And we'll say that this is in lowest terms. We'll say it's in lowest terms if the p of x and the q of x, the top and the bottom in other words, have no common factors. Now this is the same thing, the same idea that we used when we talked about rational numbers. For example, 1/3 is in lowest terms, whereas 2/6 is not, because 2 and 6 have 2 in common as a factor. The same thing goes here, except we're talking about polynomials. In the case of a rational function, which is a division of two polynomials, a quotient of two polynomials, it's said to be in lowest terms if the top and the bottom have no common factors. Now, what's nice about that is, note, if you know that you have your polynomials top and bottom in lowest terms, when r of x is therefore in lowest terms, we get a very nice fact here. The zeros of p of x, which remember is the top of the rational function, are exactly the zeros of the rational function. So you don't have to look any further. You can look at the polynomial on top, find its zeros, and in the previous segments we know how to do that, and you'll have the zeros of the rational function. Now that only works if the rational function's in lowest terms, but that makes things a little bit easier. Now you might ask, what about the zeros of q of x on the bottom? What do they tell about the rational function? Well, we'll examine those later. Don't worry. We're not leaving those out. But if the zeros of p of x are known, then you know the zeros of r of x. And that makes sense. How can a fraction be 0 after all? Only if the top is 0. Here we're looking at general rational functions. Let's go ahead and recall something that you know. This is perhaps the simplest possible rational function. This is f of x equals 1 over x. Now we did this in the library of functions earlier, and you've seen it before. It's a very familiar function, I hope. The graph of this looks something like this. There's the x and the y-axis. The curve comes up and approaches the y-axis from the top and the bottom, but never reaches it. Same thing with the x-axis. Now we'll talk more about that later. But that's the picture you should remember. You should remember that the domain of this function is the set of all the real numbers except the one that makes 0 division. X can't be 0. You also notice from the picture that it has no x or y intercepts. We'll examine that again later. And, just for the record, as x approaches 0 from the left, say, so we're coming in from this side to 0. As it approaches from 0, what does the function do? Well, clearly the function is going down. So we can say that f of x is going down to minus infinity. And as x approaches 0 from the right, it's clear that f of x, if we come from the right, the function is going up. So it seems to be going up to infinity. And of course, the infinity here, I won't write plus infinity, I'll just write infinity as always. Now, these ideas here, although they seem obvious from the picture, are helping us to begin to introduce some notation here. If we had calculus, you'd have some new notation that would indicate left and right. But I think we can just write the words out here, and we'll be fine. Now, this was one from the library of functions. 1 over x, we've seen it before. Let us now look at another one that will add to our collection of standard functions that are rational. H of x equals, very simple variation, 1 over x squared. Now before I do anything, think about what that would mean. 1 over x, let's see. If x is positive or negative, that will change the way that 1 over x looks. However, with the 1 over x squared, it will always be positive, except that one annoying case when the division by 0 occurs. So the domain of h is again the set of all the real numbers except x can't be 0, as before. Again, it's going to have no x or y intercepts, because there's no way the right-hand side can ever be 0, and that's when y would be 0, and that can't happen. And when x is 0, well, x can't be 0, so that eliminates both the x and the y intercept possibilities. And as we just noted, h of x is greater than 0 always. So with that in mind, you can construct a fairly accurate picture, and you can go ahead and look at your calculator for this if you like. But this is the kind of picture you'll get. It's as though the 1 over x for positive never changed when you square it. It did change a little, but it's hard to tell. In fact, you might want to plot 1 over x and 1 over x squared next to each other on the same picture, on the same window on your calculator to compare them. That hasn't changed much, and what was formerly negative down here is flipped up and become positive. And we can say also that as x approaches 0 from either side, so that is from the left or from the right, what does h of x do? H of x, of course, grows to infinity. So there's a little analysis of a slightly different version of 1 over x, the 1 over x squared, and that will just give us more information to deal with the harder ones coming up. So let's go do an example here before I leave this, just to put together a few things that I know you know, but we'll remind ourselves of. We can graph at this point a little bit. We'll learn more about this later. But r of x equals 1 over x minus 2 squared plus 1. Now we're going to learn how to analyze this a little bit more directly. But in this part, we can say, we can do a solution by hand easily. And we do it by analyzing the shifts and the compressions and stretches and other changes that go on, starting with a familiar function. Now the familiar function I'm starting with this time is 1 over x squared, the one we just looked at. So the graph of that looks more or less like this. And here's 0 down here. Then the next version I will look at is, say, 1 over x minus 2 squared. So putting my arrows here. What does that do? Well, I replaced x by x minus 2. So this is a horizontal shift, rightward by 2. So my little picture here begins to look more like this, where I've shifted over to 2. And so now what used to be the y-axis is there, and the curve is now approaching it. That's the line x equal 2 to be exact, just as it approached the y-axis before. And finally, to complete it, this was a very easy one, 1 over x minus 2 squared. Now I want to add 1 to it. So 1 over x minus 2 squared plus 1, and that is the final version that I was looking for. So what does that do? That's a vertical shift upward. So the picture now becomes, here's a height of 1, and instead of the x-axis being the place it approaches, it'll now be that line that it approaches. Here again is the 2 that it is approaching. And so now the picture looks something like this, having been shifted over and then up. So that's a 1 there, if you can see that. And so there we have it. There's the picture, and I've built it up by little graphs, the step graphs that we've done before. All I've done is 2 shifts, to be exact, a horizontal shift by 2 and a vertical shift by 1. Now, you notice these dotted lines that sort of stand for what the x and y-axis used to stand for? Those are going to be important. And coming up in the next section, we'll start giving those names. So let's do that. Well, we saw in the last example, but now we'll go ahead and answer that mysterious question, what is an asymptote? Strange word, isn't it? Well, it's an old Greek word that has come down to us because it's useful. And as you'll see, it's a very simple idea. So, what is an asymptote? Well, first let me go ahead and get on this page that last example so we can talk about it, because it's a nice illustration. The last example was r of x equals 1 over x minus 2 squared plus 1. And I'll re-sketch the picture we had at the end. Well, here's 1, and here's 2, so that's 1. And that represents where the x-axis used to be, and this represents where the y-axis used to be before the shifts. And then the graph looks something like this, symmetric on either side of that. So that was the graph we had. And now that we have this again in front of us, let's go ahead and make some observations that we can then generalize into a definition of what an asymptote is. And there are various kinds of asymptotes. So observe here, first thing, as, and I'll write it this way, as x approaches negative infinity. So I'll write a big arrow like this going to the left. I hope that makes that clear for you. As x approaches negative infinity, meaning going to the left, r of x does what? Well, look at the function. As you go leftward, the function's coming down, but it's not getting lower than 1. It seems to be approaching this line at 1. And what is that line? That is the line y equals 1, isn't it? So r seems to be approaching 1, that line y equals 1. And it's approaching 1 from above. Just to see what's in the picture. And let's see now. Going from left to right, we've covered this region down here. Now I'm going to cover what's happening around 2. And as x approaches 2, that's from the left or from the right. So x can approach 2 from either side. My little arrow in there. Then what is r of x doing? R of x clearly is going up to infinity in both cases. See, it's going up here to infinity. So that's happening around this line here, which of course is the vertical line x equals 2. And then finally, as x goes off to infinity, over to the right, grows without bound to the right, then what's happening to r of x? Well, r of x is again going down to 1 from above. Now I'm talking about this region over here. So what we've done is we've examined all the interesting parts. This part over here on the left, this part up here, and then this part over here on the right. And the right and the left are symmetric, except that x is going to negative infinity and positive infinity. And then something happens nicely here around 2. So with all of that in mind, we can start defining what we're seeing here. These lines that the graph is approaching, these are what we're going to call the asymptotes. Asymptote, therefore, stands for line. So let's start with the definition. There'll be 3 parts to this definition. Here's part 1. If, as, let me write my little arrows again, as x goes to negative infinity, so we're talking about big arrow to the left, or as x goes to infinity, in this case it's a big arrow to the right, if, as one of those 2 things happens, the value of r of x does not go to infinity, but actually approaches some real number. In the previous one, it approached the line 1, y equals 1, a fixed constant. The L is a fixed constant. Then we say the horizontal line, which is y equals L, there's the line there, is a horizontal asymptote. Asymptote. Yes, there's a P in there. And yes, it's a silent P. Asymptote, the P doesn't get pronounced, it seems like. For the graph of y equal r to the r of x. So this line is called an asymptote. It's still a line. It's a horizontal line. But it's called an asymptote if it is a line that the graph seems to be approaching as x goes far out to the right or far out to the left. And just to get you a little more visually oriented here, I've drawn a little picture. Bring that picture down here. There's my picture. And here's the picture I've got. Here's the x-axis down here. And I imagine x is going out to the right or out to the left. And here, up here, I put L up here as a positive y number, but it doesn't have to be. It could be an L down here. But let's just put it up here for the sake of argument. Here's L, and here's the line y equals L, the y equal L line. Now notice what R can do. R can approach it from above to the left, or approach it from below at the left, approach it above from the right, or below at the right. Now it's not going to do all of these at once, but some selection of these are what's possible for the function R. In fact, here are the possible combinations. The line y equals L has a slope of 0 because it is a horizontal line. And here are the possibilities. In short, in sort of diagrammatic form, the graph can approach that horizontal line up from the left and down from the right, or down on both sides, or the reverse of what went before and the reverse of what went before. It could also do this. There's no reason on earth in this case that it cannot intersect the line. So it might actually wave around that line as it approaches it. And it may wave around as it approaches it the other way. So those are the possible combinations for a horizontal line, which we'll call an asymptote. All of those things can happen. Okay. Well, let's continue the definition and look at part 2 of the definition. First, we saw a horizontal asymptote. Now you might expect we'll look at another direction. If, as x approaches c from the left, or as x approaches c from the right, so here's c and here's x approaching c, if either one of those two situations occurs, if x approaches c from the left or the right, if, as that happens, the value of r of x, whether it's positive or negative, let's say absolute value, grows without bound, goes to infinity, so it either goes up or down, then, if that happens, then the vertical line x equals c, the line that cuts right through that c value and is vertical, is what we call a vertical asymptote. Asymptote. There it is again. For the graph of y equals r of x, the same function, rational function that we've been looking at. So if there is a number somewhere on the real number line, some real number x, some real number c sitting there, and as the function approaches, as the x values come in on either side, the value of the function blows up, either going far up or far down, then that vertical line is a vertical asymptote for the function. And once again, to give you a visual idea of what's going on, here is a picture for you. Okay? This is vertically oriented now. So here's my y-axis at the left, and here is the x-axis running here, and here is the point C, an x value. I put it on the positive side, but it could be on the negative side also. Here is C, and here is the vertical line x equals C, the x equals C line running through it. Now notice what are the possibilities for R. R can approach and go upward on the left, or it can go downward on the left. It can go upward on the right or go downward on the right. Now again, it's not going to do all four of these at once, but those are all the possibilities. And over here on the right, I've got the possible combinations with the slope. Since it's a vertical line, of course, the slope is undefined in this case. And here are the possibilities. It can go up on the left, down on the right, reverse that. It can go up like 1 over x squared on both sides, or it can go down on both sides. And those are the only four possibilities for a vertical asymptote and the graph that goes with it. Okay. Well, with that in mind, we'll go on to the third part of the definition. Definition part 3. You might ask, what's left? Well, we've done horizontal, which is like this, vertical, like this, and now all the other lines we can call slanted lines, or oblique lines is a word that's often used. And here is the definition that goes with that. If, as x approaches minus infinity, again, I'll go ahead and do my little arrows here, or x approaches infinity far to the right, if as, if as that or that happens, the value of r of x, now, instead of approaching infinity, which would be vertical asymptote, or approaching a constant, which would be a horizontal asymptote, now it's going to approach a line, which is neither vertical nor horizontal, so I'll have to write it as mx plus b, where m is not 0. So we're not talking about a constant, which would make it a horizontal line. We're talking about some slanted or oblique line. Then the line, which is y equals mx plus b, that line is what's called, and I've used the word already, an oblique asymptote. As opposed to a vertical or horizontal asymptote, this is an oblique asymptote for the graph of r of x. Okay? So that's the slanted case. And let me again give you visually the possible pictures that you might get out of this. Here are the possible combinations for a slanted case. You could have slanted with the slope positive, so they're all going up to the right, and they can approach both from one side or one or the other side, and so you get 4 possibilities. Or the slope could be negative, so they're slanting down from the left. And of course you can do both on one side or on opposite sides in these 4 fashions. So these are small schematic pictures of what things might look like if you had a function, rational function, with an oblique asymptote. Now we're going to see these as we go on with examples, but I want you to keep these pictures in mind. Finally, let me pull together some remarks, some of which are implicit in what we've already said. Remarks about asymptotes. So for r of x, which is a rational function now, there are no asymptotes, remember, for polynomials. Polynomials go up to infinity or go down to infinity as you go far right or far left. That's all that can happen. But for rationals, these other cases that we've seen can happen. And let me say, in plain English, an asymptote, no matter the strangeness of the word, an asymptote is a line. That's all it is. It is a line that, and we might say it this way, that part of the graph eventually, if you go out far enough, or you approach, in the case of a vertical line, you approach that C closely enough, eventually approaches, but never touches. Okay? Now, realize that I said part of the graph will approach but never touch. I'll come back to that in a moment. Let me build a little chart here to show you the types and possibilities. Here are types of asymptotes, and this is the possible number of them. So you'll be aware in a given situation with a rational function of the only things that can happen. Type and possible number. Well, the types are the ones we've seen. Vertical, horizontal, and oblique. So those are the only 3 types of asymptotes, right? These are asymptotes. And how many can there be? Well, vertical asymptotes, there can be none, or 1, or 2, or 3, etc. There can be any whole number of vertical asymptotes. However, for horizontal and oblique, they're limited. Horizontal, there's either 0 or 1, and for oblique, there's either 0 or 1. And that's all that can happen. So if I box this in here, those are all the possibilities. Horizontal and oblique, there are either none, or there's at most 1. Vertical, there can be as many as you like. And a couple more remarks before I leave this first segment on rational functions. Of course, when you think about it, this has to be true. Of course, no part of the graph of R of x, of course, ever intersects a vertical asymptote. Now, it turns out that it can intersect more than once a horizontal asymptote or an oblique asymptote, but it cannot intersect a vertical asymptote at all. Why? Well, the quick answer is, if it intersected a vertical asymptote, then it would violate the vertical line test for a function. What we would have is something that's not a function anymore. Remember, for a vertical asymptote, we have a point C where the function goes to infinity. The function's not defined there. So here's your vertical asymptote. If suddenly it crosses through there, suddenly it's not defined and it is defined. You can't be both at once. So if this is the C, you see why this can't happen. So the graph will never intersect a vertical asymptote, which is nice. They form vertical walls between pieces of the function. And just to complete my statement, as I said above, but the graph may intersect. It may intersect horizontal, or let's just put it this way, non-vertical asymptotes. So that includes the horizontal and the oblique ones. And that will happen, and sometimes we want to know when that happens so that we can help us with our graphs. One other technical note before I leave this segment on general rational functions is that when you try to graph rational functions on your calculator or on a computer system, you'll find out that the asymptotes do not immediately appear. If you want them to appear, you'll have to graph them yourself as separate functions. So just keep that in mind. And now it's time to go on and discover how we can find these asymptotes now that we know what they are. We've answered the question, what is an asymptote? And now we want to address the question, finding asymptotes of rational functions, actually going about locating those once you have a rational function. So let's do that. Now let me start by recalling what a rational function is, so we'll have it in front of us here. Recall that R of x, which is what we're letting stand for rational functions, we have written as a p of x over a q of x, both of them polynomials. And let's get a little more specific now by actually writing out polynomials for them. So the top one maybe is a n x to the n plus all the way down to a1x plus a naught. And let's make the bottom one b sub m, a x to the m. So the n and the m are possibly different, down to b1x plus b naught. So here's the more general version where we have specified the labels we'll use for the coefficients. And so of course that means that the degree of p is n, the highest degree here, for the top, and the degree of q, the bottom, will be m. And then we'll examine what the differences between n and m tell us about the asymptotes of rational functions. Okay. Well, let's start out with vertical asymptotes, because we can get a nice theorem for that right away without any hard work. Vertical asymptotes. So we'll look at that first. And like I say, I'll start with a theorem, which will tell us just when exactly we can find them. So, if R of x equal p of x over q of x, as before, is a rational function, in lowest terms. Now there's a crucial phrase, in lowest terms, which remember means that the top and the bottom, the p and the q, have no factors in common. If it's in lowest terms and x minus r, where r is a real number, x minus r is a factor of that bottom, is a factor of q of x. So that means that x minus r being a factor of q of x means that r is a 0 of q of x, because putting r in for x then would give us 0 as one of the factors of q of x. So that r is in fact a 0 of q of x. And I think I said earlier we'd be talking about the zeros at the bottom, and now we finally are. Then what's the conclusion for all this? The conclusion is that if you take the vertical line x equal r, that vertical line is a vertical asymptote. A vertical asymptote for r of x, the rational function we began with. So, if you have a rational function and a top and a bottom, and this rational function is in lowest terms, which is a crucial point, then if x minus r divides the bottom, then x equals r is a vertical asymptote for the function. Now let me show you an example where the lowest terms fails and you don't get a vertical asymptote, because I think you need to see this. So I'll give you, say, a counterexample to the guess that maybe that lowest term business is not necessary. Counterexample. Here's the function r of x. It is x plus 1 over x squared minus 1. Now you know the bottom factors, so let me do that. X plus 1 over x plus 1 times x minus 1. Now, this is not clearly in lowest terms. Right? Because the factor x plus 1 is common to the top and the bottom. So this is not in lowest terms. So, although, I'm writing out a lot here, but I want to be clear, although x plus 1 is a factor of the bottom, which is the q of x, x equals minus 1, so if this is the x minus r format, then minus 1 is the r. X equal minus 1 is, I'll even box that in, is not a vertical asymptote for r. Okay? This is not a vertical asymptote. And let me convince you of that by looking at the graph and show you what does happen. So I'm graphing this on minus 3 to 3 by minus 3 to 3, in case you want to reproduce this. And here's the picture I got. And it's nice and symmetric in the axes. Over here at 1, there is indeed a vertical asymptote. Now that part's okay because x minus 1 is not common to the top and bottom. So that x equal 1 there actually does give an asymptote, a vertical asymptote there. And the curve looks like that around that. The curve otherwise, here's minus 1, looks like this. There's a hole at minus 1, and then this continues on down and approaches 1 from the left. So 1 turns out to be a legitimate asymptote, and minus 1 is not a vertical asymptote, as you can see from the graph. Okay? You will have a hole there because, yes, division by x plus 1, where x is equal to minus 1, is division by 0, so that is not in the domain of the function. Now, I have to tell you that on your graphing calculator, you may find it difficult to see this hole, but ideally there should be a pixel missing there. Even if there isn't one there, you know one's there. So you need to indicate that on any graph that you draw by hand. But this is what will happen. If you don't have lowest terms, part of the theorem, then you won't get a vertical asymptote. All that will happen is you get a hole in the graph. And again, remember, this vertical asymptote I had to draw in by hand because that will not appear on your calculator. Okay, with that theorem and that counterexample at the back of your mind, here's time for you to try one for yourself. Why don't you try this one? R of x is equal to x over x squared minus 4. I want you to find the vertical asymptotes and produce a graph that shows the vertical asymptotes and the rest of this value of this function. So I'll come back in a moment. Well, I hope you didn't have too much trouble with that. Here is the function as you see, the rational function. And you may have noticed right away that the bottom is the difference of two squares. So we can factor that, and I'm going to do that right away. X plus 2 times x minus 2. And you might also notice, once you have that or before, that the top and the bottom have no common factors. So that means that r of x is in lowest terms. Well, since it's in lowest terms by the previous theorem, x, the factors x plus 2 and x minus 2 divide the bottom, the q of x, the x squared minus 4. So that means I immediately get, so x is equal to minus 2 and x equal to are vertical asymptotes. And there you have it. It's just that simple. Of course, we didn't have to put this in lowest terms, so that was nice. But the rest of it, and also the bottom factors nicely, which I admit is nice, but now we see that those are vertical asymptotes. Let me show you what they look like in a graph, because we did want to see a graph. And I'm using the same interval I've seen before, minus 3 to 3 by minus 3 to 3, the window we've seen before. And here is the picture that I got. My axes are sitting there nice and symmetrical. Here at 2, I have one asymptote, and at minus 2, I have another one. And what is the function doing around those asymptotes? Well, it's coming down like this, coming down here, touching in the middle and going down, and coming up over like that. And remember, I drew in both of these asymptotes by hand because the calculator won't do it unless I specify it, and I didn't bother to in this case. Horizontal asymptotes. Well, there are some similarities and differences between this and the vertical asymptote case. But before I get into them, I need to bring you up to date on a piece of terminology that we used before for rational numbers that we're now going to use for rational functions. Recall, way back in Q, remember what Q stood for? It was the set of rational numbers. If P and Q were in N, meaning they were natural numbers, then we looked at P over Q, a typical element of Q, the set of rational numbers, and we called it a couple of things depending on, well, let me show you. We called it proper if P was less than Q, if the top is less than the bottom. A fraction like 2/3 would be considered a proper fraction, whereas we called it improper if P was equal to Q or P was greater than Q. So if we had a fraction like 4 over 4, we call that an improper fraction. If we had a fraction like 4 over 3, we call that also improper. Sort of top-heavy in that case. All right, so that reintroduces the words improper and proper. Let me observe a couple of things that will affect us with polynomials. Notice the following. If P goes to infinity, what happens to P over Q? Let's suppose that Q doesn't change. Q stays constant. What happens to the fraction as P goes to infinity? Well, now this is going to become, it's going to become improper. In fact, it'll be improper in the greater than sense because the P will eventually get bigger than Q. And what happens to it? Well, it goes to infinity, doesn't it? The fraction grows to infinity if the top goes to infinity. And that's easy to see by looking at any fraction you pick out. On the other hand, suppose the bottom blows up, like Q goes to infinity. What happens to P over Q? Well, P over Q eventually becomes proper because the bottom eventually will grow larger than the top and make this a proper fraction. And what happens to proper fractions? If the bottom gets bigger and bigger and the top does not change, these fractions always go down to 0. So there's a little observation I wanted to make about fractions. If the top goes to infinity and the bottom doesn't change, you're headed off to infinity. If the bottom goes to infinity and the top doesn't change, you're headed off to 0. The improper and proper cases. Okay, let's keep that in mind. And now let's define what it might mean for a rational function to be proper or improper, just like rational numbers. Definition. Suppose R of x is P of x over Q of x, where, as usual, P of x and Q of x are now, instead of real numbers, as in P over Q, but they are now real polynomial functions. The only kind of polynomial functions we look at, real polynomial functions. This thing here is called, and here are the names, it is called proper. It is called a proper rational function if, well, now we just can't take these as numbers and compare them as P or Q being greater or less than or equal to one another. So what we'll compare instead are the degrees. If the degree of P is strictly less than the degree of Q, then we'll say it's proper. And I'll even run a line through here, and we'll say that it's improper if, well, you're probably ahead of me on this one, if the degree of P is equal to the degree of Q, or the degree of P, the top, is bigger than the degree of Q, the bottom. So there we have a translation of those words that we use for rational numbers into what they would mean for a rational function. And with the observation I made before, again, if the top, in this case, function goes off to infinity, and it's going to go there faster than the bottom if it has higher degree, that is to say, if it's improper, like it is down here, then the rational function will go off to infinity. If the bottom goes to infinity, which would make it more and more proper, if the bottom goes to infinity, then this whole thing will go to 0. 0, or y equals 0, is a horizontal asymptote. So we have those insights, and to put it in the form of a picture that I hope you'll remember, I've drawn this for you. Let's see if we can analyze this big picture. First case we'll look at, suppose R of x is proper. That is to say, n is less than m. Remember, the degree of the top P is n, the degree of the bottom Q is m. And I'm taking degree P less than degree Q. I've written it vertically, make my point. In this case, it's sort of bottom heavy, right? The bottom has higher degree. Now here's the x-axis, which is the line y equals 0. I've labeled it at both ends. And as x goes to infinity or x goes to minus infinity, what does the function R of x do? Well, it either comes down to that asymptote, that y equals 0 line, or comes up to it, and the same thing on the right, comes down or comes up. This is a horizontal asymptote, the line y equals 0, which we also call the x-axis. So if R of x is proper with the n less than the m, the top degree less than the bottom, then there is a horizontal asymptote for this rational function, and it is y equals 0. So let me give you an example of such a rational function that has this kind of picture associated with it. Here's the example. R of x is equal to x minus 12 over 4x squared plus x plus 1. Now this is clearly proper since, just to argue it correctly, the degree of the top is 1, and that's less than 2, which is the degree of the bottom. Okay? So we have a horizontal asymptote. We have a horizontal asymptote, which is the line y equals 0. And that's all there is to it. If you were just looking for horizontal asymptotes and nothing else, you now know that that's what that rational function has. But I want to show you something else. In addition to the picture I just showed you, I want to go ahead and give you another way of thinking about this, which will justify again that this is really right as a horizontal asymptote. Here's an idea that's sort of behind what's going on. Suppose I take this R of x, let me write it down again. X minus 12 over 4x squared plus x plus 1. And imagine that I look through this, top and bottom, and I find the highest power of x. That is x squared. And now suppose I multiply top and bottom by 1 over x squared. 1 over x squared, 1 over x squared. Now this is just to make my point, so watch what happens when I do this. When I do this, the 1 over x squared on the top leaves me with 1 over x minus 12 over x squared. And on the bottom I get 4 plus 1 over x plus 1 over x squared. So I have a top and a bottom that look like that. Now why would anyone want to do that? Well, you wouldn't if you were trying to simplify. But look at the point I'm going to make now. Now, as x goes to infinity or as x goes to minus infinity. That's one way to write that. Sometimes this is written as the absolute value of x goes to infinity to encompass both of them. In any case, when that happens, what happens over here? All of these 4 fractions have a denominator involving x, but the numerator, the top, involves only a constant. If the x grows, what happens? The r of x here, which has simply been rewritten, approaches 0. This 1 over x goes to 0, minus 0, that goes to 0. The bottom goes to 4, plus 0, plus 0. Well, what is that? That's 0 over a non-zero number. That's the number 0. And that's the y equals 0 asymptote that we just claimed was there. So you can check this yourself. Now, I don't expect you to do this calculation down here. Don't worry about that. This is strictly to show you that algebraically I can convince you that as r of x, as the x grows, whichever way you want to think about it, as the x grows, the r of x will approach 0. And this is algebraically why. The picture from before, the picture I had up there before, this picture tells you visually why. As x goes to infinity and negative infinity, the function r of x is approaching the y equals 0 line. Okay, good. And if you wanted to graph this, we might as well not leave this problem without graphing it, just to show you that the horizontal asymptote really is y equals 0. Go ahead and show you the graph, just to convince you. I graphed this on this window, minus 5 to 5 by minus 13 to 1 with a little thought. And here is the picture that I got, which you can generate on your own if you like. There are my 2 axes. Now, remember, this is the x-axis, so this is the y equals 0 line, or the x-axis. And here's what the function looks like. It has this big dip in the middle, it's symmetric on both sides, and it approaches the axis from both sides. So you can check that out on your own if you like, but that just confirms what I said a moment ago. Okay, this was the case where r was a proper rational function. Proper. And it went to a horizontal asymptote y equals 0. Let us look at one of the improper cases. And here's my picture that goes with that. If r of x is improper, but we're looking at the one case where n is equal to m, that is to say the degree of p equals the degree of q. Suppose the degrees are equal. Now what happens as you go out to the left or to the right as x goes to infinity on the x-axis? Well, it turns out that r of x will approach a horizontal line again, but it will not be the x-axis. It will not be the 0 line. It'll be a line that I've labeled y equals L temporarily, y equals L. And you see that r of x will approach from above or from below on either side. Now, here I've written that the L is in fact a sub n, the leading coefficient on the top, over b sub m, the leading coefficient on the bottom. Now, of course, in this case, n and m are the same. So it is simply the leading coefficient of the same power of x top and bottom. This gives you a horizontal asymptote, y equals a sub n over b sub m. That won't be 0. That won't be the x-axis. It'll be a horizontal asymptote somewhere else. Let me illustrate that by doing an example to show that fact. Here's r of x equals 8x squared minus x plus 2 all over 4x squared minus 1. Now again, I'm only looking for horizontal asymptotes. I recognize that this is improper, and this is an n equals m case of improper. The degree on the top and the bottom is 2. So that means immediately I know that there's a horizontal asymptote. And what is it? It is y equals, the leading coefficient on top is 8, the one on the bottom is 4, so y equals 8 over 4, which simplifies to 2. So y equals 2 is the horizontal asymptote. If that's what I was looking for here, I have now found it. Once again, let me show you an idea with a little algebraic calculation to convince you that that really is the right answer as the x's grow to both sides, as the x's go to the left and the right. Again, I'll do the same kind of calculation. I take r of x here, 8x squared minus x plus 2 over 4x squared minus 1. The highest power here, of course, is x squared. I multiply the top and bottom by 1 over x squared. And on the top, I will get 8 minus 1 over x plus 2 over x squared. On the bottom, I'll get 4 minus 1 over x squared. Then, as the absolute value of x goes to infinity is another way of just saying that x grows either left or right, grows without bound. Then what happens to r of x? R of x goes to 8 minus the 1 over x. As x grows, will go to 0. The next term will go to 0. The bottom is 4 minus 0. So this goes to 8 over 4, which of course is 2. That's y equals 2, the horizontal asymptote I was talking about. So again, you will not have to do this calculation. Don't worry about it. All you have to do is recognize that if the degrees are the same, take the two leading coefficients, put one over the other, and you've got your horizontal asymptote. Now, graphing it, of course, is another story. Let me show you what the graph of this looks like. Here's the graph. And my window is minus 3 to 3 by minus 5 to 5. That seemed to work out reasonably well. Here's the picture that I got. Again, my axes are symmetrical. And I said there'd be an asymptote at y equals 2. So that is the y equals 2 line. And the picture looks like this. Curves down there. Looks like this. Now this may well have other asymptotes. The only asymptote I was looking at in this case was the horizontal, but it suggests from the picture that there might be a couple of vertical asymptotes. We can look at those at another time if you like. Okay, we've looked at vertical asymptotes and horizontal asymptotes. There's one more case, oblique asymptotes. But before we get to those, I wanted you to have some time to practice these horizontal asymptotes. So we'll stop here for a moment and I'll be back. Now that you've had a chance to look at horizontal asymptotes, let's finally look at the last case, these oblique asymptotes, which are the ones that are slanted. They're neither vertical nor horizontal. So this will be the last improper case. The last improper case. And that is the case when the degree of p is greater than the degree of q. Now p was the top of the rational function and q was the bottom. And so that was n greater than m. If you remember, we labeled the degree of the top n and the degree of the bottom m. And luckily, there's a fact here which will limit the kind of work we have to do. Only when the degree of p is 1 more than the degree of q will we have an asymptote. Otherwise, we'll have functions that the curve will approach, but they won't be lines, so we won't call them asymptotes. So here is the fact that will make that happen for us. Fact, only when n equals m plus 1, 1 more than the bottom, does r of x have an oblique, or slant if you like, or non-vertical, and non-horizontal to be clear, non-vertical and non-horizontal, asymptote, and that's it. If n is greater than m plus 1, there are no oblique asymptotes. There will be curves that the given function will approach, that's true, but they will not be asymptotes. Asymptotes, remember, are lines. So when n is 1 more than the bottom, when the top has degree 1 more than the bottom, you'll have this oblique case. Let me show you my visualization of this as I did with the other cases. If r of x is improper and n is m plus 1, so the degree of p is equal to the degree of q plus 1, which makes the top heavy, then as x goes to infinity or x goes to minus infinity, r of x will blow up to infinity or blow down to minus infinity in both cases, left or right. So an oblique asymptote will be some line, ax plus b, and the way we'll get this line, here's the hint that's coming up, we'll get it as the quotient function, which results when you do a division. So let me give you an example to show you how this would work. Example, r of x equals 3x to the fourth minus x squared over x cubed minus x squared plus 1. Now you can see from there that the top degree is 4, the bottom degree is 3, and as a result, the top has degree 1 more than the bottom, and so that is exactly our improper case, where degree of p is 4, and that's exactly 3 plus 1, which is the degree of q plus 1, and that's what we wanted. So an oblique asymptote exists. So an oblique asymptote exists. How do we get it? Well, we have to divide. We have to divide to get the quotient function, which will be that y equals ax plus b. And once we get the y equals ax plus b, that will be our oblique asymptote. So let's do the division. We've done these divisions before. Let's do another one. Our function is 3x to the fourth, and I'll put a little space here, and minus x squared. And we want to divide into that the bottom, which is x cubed minus x squared plus 1. And what we get on the top, remember, will be the quotient function that we're looking for. So this will be the quotient function when we get done. Well, let's see. We need to multiply x cubed by 3x to get 3x to the fourth here. And then what else do we get? We get minus 3x cubed plus 3x. The algorithm is to subtract that away from the one above. That leaves a 0 here by design. In the middle we have only one cubic, so that'll be 3x cubed. We will not forget to bring down our squared, minus x squared, and then we'll have minus 3x. Again, we need to multiply by something. This time we'll multiply by plus 3. That's 3x cubed minus 3x squared plus 3. Subtract that away. The first one is 0 by design. The second one, we have plus 3x squared minus x squared. So we have 2x squared. Bring our minus 3x down, and then minus 3. This degree is lower than this degree, so we are done with the division. This part down here would contribute to the remainder function, but I'm not interested in that. I'm only interested in the quotient function. So that is to say that r of x is equal to 3x plus 3, that's the quotient function, plus the remainder function, which I don't care about right now. I will mention one thing, though, so that you can see why this is indeed an asymptote. The remainder function is constructed by taking this last polynomial of degree 2 and putting it over the divisor of degree 3. That is a proper rational function. And you remember what happened to those as x went off to infinity. They went to 0. So this will approach, this will be the asymptote that we are looking for. This will be the oblique asymptote in this case because it's not vertical or horizontal. And the remainder function will go to 0. So if you want to see what this looks like in a picture, let me go ahead and show you what I ended up with. Here's my graph for this case. And what I first looked at was minus 3 to 1 by minus 5 to 4, that window. Here's the picture that I got. And I'm drawing in the asymptotes again now. Here are my axes. Now I know the asymptote, if you remember, was y equals 3x plus 3. So that has slope 3 and crosses y-intercept 3. So mark off 1, 2, 3 here. So I know it crosses there. and it will cross back here at minus 1, and I'll draw that in, dot that in, because that won't appear on my picture. And then when I draw the rest of the graph, I get something that looks a little bit like this, curve like that, and then a curve that comes out like this. Now, it certainly suggests that there's another asymptote there, a vertical asymptote, somewhere around a minus 1/2. We're not looking for that now, so we'll leave that till later. This is 3x plus 3, the oblique, and this is the left end of that asymptote and how it approaches. Now, if this is really an asymptote, it ought to be approaching from the right end too. The problem is on this scale I can't see that. So what I'm now going to do is I'm going to change my window to minus 0.5 to 3 by minus 5, and now I'll go all the way out to 15. Instead of going only out to 4, I'll go out a lot farther. And now I should be able to get a picture of what the right end looks like. And here are my axes this time. Here is that 3 perhaps, like that. The asymptote runs up something like that, say. And the curve, when graphed, you get something that looks like this. And notice that it actually crosses that line. So this is still the line y equals 3x plus 3, the asymptote. But now we have a crossing point. And that occurs at x approximately 2.18 if you want to check that out. This is the right end. So the oblique asymptote, the curve is going to approach it at both ends somehow. And you won't always see that happen on one scale. You may have to change your scales. And when you do that, you'll find out that sometimes it'll cross its own asymptote, which can happen, remember, for non-vertical asymptotes. So here's a case in point, and we'll be looking at more of those as we look at more examples. But before we leave this segment, let me give you a summary now, because there's been a lot of information. Here's a summary of all this information about asymptotes. First line says it all. Asymptotes are lines. Asymptotes are not other kinds of curves. R of x, rational function p over q with the a n's and the b m's down here, just as we've set before. If r of x is in lowest terms and x minus r factors the bottom, q of x, then x equals r is a vertical asymptote. If the degree of the top is less than the degree of bottom, y equals 0 is a horizontal asymptote. If the degrees are the same, y equal an over bm is another horizontal asymptote. If the degree of the top is 1 more than the degree of the bottom, then when you divide, you'll get a quotient function. That function will be linear. That'll be that extra degree. And that will be an oblique asymptote. I'm sorry, that's kind of blocked out a little bit down here. It's an oblique asymptote. And if the degree of p is greater than the degree of q plus 1 and is greater than m plus 1, there are no horizontal or oblique asymptotes at all. They don't exist. So that's the complete summary. And I think we'll pause now, and when we come back, we'll try and graph rational functions and put all of this together. Now we're going to put it all together and see how we can graph a rational function, look for all the various types of asymptotes and the other aspects of that function, like x and y intercepts and the like. So this will be graphing rational functions. So I've started out here, and I've written up a sort of summary of what we know about rational functions, and now we're going to apply all of this. So I thought I'd remind you. Once again, r of x is p of x over q of x. That's a n's and b m's on the bottom for the two polynomials. X-intercepts, of course, are x0. That's what they look like in their graphical form. And how do I get x-intercepts? What I want to know when the function is going to go to 0, that's going to occur when we look at zeros of p of x. Now I ran out of room here, so I've written this out, zeros of p of x, but not zeros of q of x. It's usually easiest to find these zeros when r of x is in lowest terms. But as long as you've got the zeros of p of x and these zeros are not also zeros of q of x, you're fine. And they will be the zeros that will give you x-intercepts. Y-intercept will be, of course, the point 0, r of 0. R of x in lowest terms, if you have that situation and r is a 0 of the bottom, q of x, then x equals r is a vertical asymptote as we saw before. If r is not in lowest terms, be very careful. Zeros of q of x might be wholes. They might be vertical asymptotes, it's true, but they might be wholes also. Okay? Then, what else do we remember from what we did previously? If n is less than m, that is the degree of the top, remember, is n, the degree of the bottom is m, then we have y equals 0, horizontal asymptote. If they're equal, y equal a n over bm is another horizontal asymptote. If n is 1 more than the bottom, m plus 1, the quotient function upon division gives you an oblique asymptote. And if n is bigger than m plus 1, there are no horizontal or obliques. And now let me add a couple of things we didn't do there, but we will do now. If you want an r of x intercept with the horizontal asymptote, what do you check? Well, you simply set r of x equal to the horizontal asymptote, which, as you see from above, could be 0 or a n over bm. And if you want it to intersect the oblique asymptote, you do the same idea. You let r of x equal the quotient function that you get upon division, which is the oblique asymptote. So with that little summary in mind, let's go ahead and look at some examples where we put all of this together. Example, and there'll be one here a little bit for you to try. R of x equals x minus 1 over x squared minus 4. Now, you want to graph this and include all the information that we can gather on this. Now, certainly looking at this, my first instinct is to factor the bottom, so that's what I'm going to do. The top I'll simply rewrite as x minus 1, and the bottom I will factor into x plus 2 times x minus 2. Then, I'll start looking at things. X-intercept. Well, having things factored, I see that the top and the bottom have nothing in common, no factors in common, so this is in lowest terms. So all I have to do is find the zeros of the top, and I will know exactly where there are x-intercepts, because those are the zeros of r of x. And it's immediate that this is x equals 1 is such an x-intercept. Y-intercept, well, let's see. That, remember, is the point 0, r of 0. So I'll compute r of 0, which means substitute 0 in. On the top, I get 0 minus 1 over 0 plus 2 times 0 minus 2. Getting rid of all the zeros, I simplify and I see that the bottom gives me minus 4. The minus on top then gives me plus 4, so I have 1/4. And so the point in question is 0, 1/4. That's my y-intercept. Now again, having noticed that r is in lowest terms, I know that x equals 2 and x equal minus 2, the places where the denominator, the q of x, goes to 0, are vertical asymptotes. So that is immediate again from what I've got written above. So you can get a lot by simplifying. Okay. What else can we say? Well, the degree of the top is less than the degree of the bottom. Okay, we got the vertical asymptotes by looking at just the bottom, but now we examine it from the point of view of degree of top. Degree of p, which is 1, is less than 2, which is the degree of q, the bottom. So we have a horizontal asymptote. And that horizontal asymptote, since the top is less than the bottom, is y equals 0. So that's a horizontal asymptote. So we've got two verticals and a horizontal. And we've pretty much got the information we wanted. We wanted to check one other thing, if you remember my summary. We wanted to know if the curve ever intersects its horizontal or oblique asymptotes. Doesn't have an oblique one here. But to see about intersection, intersect the horizontal asymptote, you might ask? Well, I will solve that, I will answer that question by setting r of x equal to 0. That's y equals r of x equal y equals 0, the horizontal asymptote. And then ask if there are any solutions. Well, what will make r of x 0? Well, we already know the answer to that. The answer is that x equals 1 will make that 0. That is what makes the top 0, the p of x, and that gives us the x-intercept, incidentally. So we do have an intersection point at x equal 1. So here's my sketch. And you know, I did this by hand. I didn't need the calculator because I really have enough information. But if you do the calculator, you'll see something similar. And I have my two axes here. I know that at 2, marking that as 2 and this as 1, I have a vertical asymptote. And then at -2, I have another vertical asymptote. And then if you draw the curve in, you get something that looks like this. Remember, it crosses its horizontal asymptote at 1, and that's the point. Its y-intercept is at 1/4. That's another point you can mark. And then if you really wanted to check the rest of it, you could take a few examples by putting some points in. And you'll see that that's what the picture looks like. Now this, remember, is the y equals 0 line, and that's the x-axis, and that's the horizontal asymptote. And if you want to check this on your calculator, here's a window I recommend. The -4 to 4 by -4 to 4 window will certainly give you a picture similar to this. Okay. Well, let's do another one. We wanted to look at a few examples here. Let's do yet another one. The example here is r of x equals x squared minus 1 over x. Now you can see that this one's different because its degree on the top is bigger than the degree on the bottom. In fact, it's 1 more, so we expect an oblique asymptote here. But again, I can't help myself. I see that there's a factorization to be done on the top, so I'm going to do it. This will be x plus 1 times x minus 1 all over x. Okay. Well, let's start writing down some of the facts we can get. X-intercepts. X-intercepts will be the zeros of the top, because those will be the zeros of r of x. In this case, where this is in terms where the top and the bottom have no common factors, this is in lowest terms. So the x-intercepts will be where the top is 0, that's x equals 1, or x equal minus 1. The y-intercept, again, just running through this, is going to occur at 0, r of 0. So I compute r of 0, which I need to do. And I have something that's undefined. Right? Because I cannot divide by 0. So that means there are none. There's no y-intercept. And now, since r of x is in lowest terms, we now can see that we have a vertical asymptote. I'm getting more compact in what I write down. Vertical asymptote, because this is in lowest terms, there'll be a vertical asymptote where the bottom goes to 0, and that'll be x equals 0. Now remember, that's the y-axis, so we've got a vertical asymptote, which is the y-axis. Then we have degree of the top, p, is 2, and that's exactly equal to 1 plus 1, which is the degree of the bottom, q plus 1. So we have an oblique asymptote. An oblique asymptote here. Now how do we get that? We get that by division. Well, luckily the division is easy. Here we see that r of x can be rewritten. It's x squared minus 1 over x, but we can divide that x into each part immediately to get x minus 1 over x. So this is my oblique asymptote, the line y equals x. And I can ask the further question, did the oblique asymptote and the original function ever intersect? That's not hard to check. So intersect oblique, one might put in telegraph form. Intersect oblique, well, I would want to solve r of x equal to x. That's the oblique. This is the original function. Well, that's x squared minus 1 over x equals x. X is not 0, so I'll multiply both sides by x. X squared minus 1 is x squared. That would leave you with minus 1 equals 0. That's a contradiction. That can't happen. So the answer is no. It does not intersect its own oblique asymptote. And then we can look at a picture. Again, I can sketch this by hand if you like. Here's the graph. And we know that there's an asymptote which is oblique, and it is the y equals x line. And we know that this will cross at 1, that's an x-intercept, and the minus 1's another x-intercept. And we know that the y-axis here is an asymptote. So the picture we get, extend this y-axis a little bit here, is something that looks like this. There's the asymptote, and then up here we have a similar picture like that. So the curve is trying to approach both the y equals x line here and the y-axis. Those are the two asymptotes. And again, if you wanted to do this on the calculator, the minus 3 to 3 by 3, minus 3 to 3, I believe, would give you a reasonable picture. So you can try that if you like. Well, let me pose a problem to you now. Here is a rational function. R of x is equal to 3x squared minus 3x over x squared plus x minus 12. I want you to graph it, and among other things, find the x and y intercepts and the asymptotes. Now, if you happen to notice anything else, like if you have a horizontal or oblique asymptote and the curve crosses it, find those points also. I'll leave that to you, and I'll be back in a moment. Well, here's the problem, and let's see if we can analyze it, and I hope I come up with the same thing that you did. Again, the first thing I'm going to do is try some factoring, and luckily the factoring won't be too hard for me. On the top I see that 3x is common, so I'll factor that out right away. And what's left? I have x minus 1 left. On the bottom you may have to think a bit more, but that's a fairly easy factorization also. Down to x plus 4 times x minus 3. Now, at a glance I can see that there are no common factors top and bottom, so this is in lowest terms. That's good. That means I can start writing things down immediately. X-intercepts, if any, they will be where the top goes to 0. And that will make the r of x, of course, 0, which will make those x-intercepts. Well, the top goes to 0 clearly for x equals 0 and x equals 1. So we have two places where it intersects the x-axis. All right, y-intercepts, or y-intercept. To do that, I need to calculate r of 0, as you know. So I'll do that, and very easily, because I'll see that I have 0 times minus 1 on the top, and then I'll have 4 times minus 3 on the bottom. And since there's that 0 on the top, I get 0. That means I have the point 0, 0 as the y-intercept. Well, I already knew it was the x-intercept, so I didn't really learn anything new here. Okay, r of x is in lowest terms, so that means immediately I can write down the vertical asymptotes. Because if it's in lowest terms, I simply look at what makes the bottom 0. That's going to be x equals minus 4 and x equals 3. Collecting lots of information. I see that the degree of the top, the degree of P, is equal to 2, and that's equal to the degree of Q, the bottom in this case. So that means I have a horizontal asymptote, and that is y equals, since the degree is the same, I take the highest coefficient on the top and the one on the bottom, so the coefficient of the highest degree rather, so I have 3 over 1. So the line y equals 3 is the horizontal asymptote. Now let's see, I want to find out if the horizontal asymptote and the original curve actually intersect. So let's gather that piece of information. So let me write that out telegraphically. Intersect r of x, or I guess the horizontal intersect r of x, something like that. Well, what I do to solve that, of course, is if I set r of x equal to 3 and then find out what I get. Well, this one's a little more complicated than the ones we've seen before. 3x squared minus 3x all over x squared plus x minus 12 equals 3. Well, the bottom has places where it's 0, but we eliminate those from the domain, so I will multiply both sides by that. And also, while I'm at it, I see that 3 is common on the top and 3 is common over here. So if I divide out the 3, I get x squared minus x over here. And then if I multiply this over here, I'm multiplying by 1. I have x squared plus x minus 12. Well, the x squareds are common, so I can subtract them away. And then I can move the x over. If I like, let's see, move this x over to here, and I move that 12 to the other side. I have 12 is equal to 2x. So that means x is equal to 6. So when x is equal to 6, this intersects the horizontal asymptote and the function intersect. Now what the y value is for that is r of 6, and if you check, r of 6, with a little effort you'll see is 3. So that gives the point then 6, 3 as an intersection point. Well, with that in mind, I can go to the picture and I can finally pull all of this together. Now you'll have this all on one page when you're doing this. Here's the graph that I ended up with. Let's see. Kind of slip everything in over here. I learned that I had an asymptote at minus 4. So there's minus 4. I had, that's a vertical asymptote. I had another vertical asymptote up here at 3. So there's 3. I had that horizontal asymptote also at 3 that I discovered. So that's running through this way. Here's my x and my y axes. I know that this, I have intersection points. It intersects the axis at 2 points. It intersects at 0 and at 1. So I have those two. And for the y-intercept, that was also the same as the x1. So with all of this in mind, if I put this in the calculator or I try some values in between, I'm going to see the following picture. The curve goes like that over there. In between here, it's very, very short above 0, 1. As you'll find out, it doesn't go any higher than 0.10. So that's a little bit short, and you may want to zoom in on that to see that. And up here, it crosses down below and then comes back up to the graph. Where it crosses is at 6. Remember, we found that point. This is 6, 3. Okay? And that's roughly what the picture looks like. Now, if there's any place you want to zoom in on, you can do that. That's something you ought to consider doing. On this first picture, I did some sort of general minus 10 to 10 by minus 10 to 10 window if you wanted to try it on your own. But, for example, you might want to zoom in on this portion here if that is not immediately clear on the scale you've chosen. You might also definitely want to zoom in on this part because that part is going above the axis. I've drawn this by hand so you can see it, but the fact is on the graph you'll see that it's very, very flat. You might want to zoom in on that so that it looks a little bit more like the piece goes up and down. So, with that in mind, I expect you to try a great number of these problems. That will finish rational functions, and it will finish this unit.